Sorry, Ken got a little tripped up because my title is different from what was advertised. It's because I have commitment issues and I always change my title shortly before the talk. So yeah, as Ken mentioned, I'll talk about neutron stars as Axion laboratories. And this is part of a broader program, which is now you see where the compact objects are coming from, which is compact objects as new physics laboratories. And the idea here is to leverage the extreme conditions in and around compact objects such as black holes, neutron stars, and white dwarfs to look for new physics. And by new physics here, I mean both extreme limits of standard model physics, as I'll talk about kind of towards the end of the talk, as well as physics beyond the standard model. And in the interest of time and scope, I'll focus on this particular question of how we can leverage the extreme conditions in and around neutron stars to search for axions. Okay, so here's just a visual summary of a bunch of work done by myself and other people, some of whom are in this room, on using neutron stars to look for axions. And I kind of want to start pick up where Libby left off, which is just to provide some kind of more details on how rotating neutron stars, also known as pulsars, can produce axions. And so this is a fun little electrodynamics problem. So you can start with a neutron star, which is just a giant magnet. And when you set it rotating, if it's a dipolar magnetic field, you set that rotating, you would induce a quadrupolar electric field. And this electric field can be so strong that it can tear plasma from the surface of the neutron star. And it does so until the electric field or the plasma can screen that rotationally induced electric field. However, this doesn't occur everywhere. There are certain localized regions called gaps that are shown by these tiny little cylinders here. And in these gap regions, the electric field cannot be screened. And so you get a kind of a revival of this electric field component parallel to the background magnetic field. And Libby went through great detail on the physics of what's going on in those gap regions. We understand that they're possibly producing pulsar radio emission. And she showed the nice plot of the QED processes that she didn't go into, but that I'll kind of go into towards the end of the talk. And so the physics of what's going on in that region has been studied extensively by plasma physicists and astrophysicists, Libby being one of them, who has this nice semi-analytic prescription for the dynamics, the highly nonlinear plasma dynamics in that gap region. And it's also been studied in great detail in particle and cell simulations done by many people that I list here. And so the takeaway is that these dynamics lead to a highly space and time varying electric field in the gap region. And this, as Libby mentioned, can give rise to axion production. And one of the main things is that unlike the radio emission being sourced in that region, axions are emitted quasi-isotropically. And by quasi-isotropic, I mean it's just not as beamed. It's not exactly isotropic, but it's not quite as beamed as the radio emission is. And the idea is that some fraction of those axions can convert into photons on their way out, and those photons may be detectable once we have a better understanding of the astrophysics of this system. So I don't generally like to show too many equations, but I think this is a little bit instructive to look at the problem of axion-photon mixing in a plasma. And so I'll take some simplifying limits, namely I'll look at ultra-relativistic axions in a 1D, 1D spatially varying magnetic field and plasma. And if you write down the equations that the axion electrodynamics equations that Libby presented, they look something like a two-level mixing problem that you would see in standard quantum mechanics textbooks. So this looks like the Hamiltonian that you would get in, say, time-dependent perturbation theory, where instead of time, we have position playing the role of time in the Schrodinger equation. And what we understand from this is that there can be just, as we get resonant excitations, we also have resonant conversion of between axions and photons. The photon here is A parallel, the axion is lowercase a. And I don't want you to focus too much on the details of this equation, but what I want to show is that this resonance occurs when the axion mass coincides with the local plasma frequency. And the plasma frequency is defined with respect to the full phase space information of the plasma. So that's shown by this distribution function here. And so to characterize the mixing of axions and photons in a magnetized plasma, we really need to have an understanding of what the actual plasma state is in this plasma. And we can also calculate something like a conversion probability, what fraction of your axions convert into photons or vice versa. I should mention this physics is actually analogous to neutrino flavor oscillations. And so there's a nice analogy there that you can kind of convince yourself of. And so this resonant conversion probability not only depends, so it depends on where that resonance takes place. It also depends on the local magnetic field where that mixing is happening. And so the basic takeaway of this slide is that I want to emphasize that really the signals that we expect from axion-photon mixing in these systems, it really depends critically, it hinges on understanding how plasma and electric and magnetic fields are behaving. So I want to examine two different kind of populations of axions that you might see emitted from this gap region. One I just mentioned are particles whose velocity is large or is ultra-relativistic. These ones, as I mentioned, they just escape, and on their way out, some tiny fraction of them might convert into radio photons. Another population, which I label V less than V escape, have velocities less than the escape velocity of the star, which in the case of the neutron star is actually significant. It's about half the speed of light. And so you can convince yourself that the fraction of phase space that's emitted into these gravitationally bound orbits goes like the escape velocity cubed, roughly. And so that's about 1 in 10 axions from a neutron star emitted here are emitted into gravitationally bound orbits. And this is also something that's been studied in other stellar systems by people in the crowd. And so what you find is that this gravitationally bound population can grow over astrophysical timescales to form an axion cloud or an axion condensate around your neutron star. And the density of this condensate, Libby quoted the number, which is about 10 to the minus 22, or sorry, 10 to the positive 22 GeV per centimeter cubed, which, if you remember the number, the local dark matter density, just as a reference, is about 0.3 GeV per centimeter cubed. So this is a roughly 20 plus order of magnitude enhancement in the dark matter density surrounding a neutron star compared to an experiment on Earth. Another interesting thing that can happen, which Libby alluded to, is that if I have a sufficiently large axion amplitude in this gap region, the axion might actually back react onto those complicated electrodynamics that Libby was talking about. And so you could examine Gauss's law in axion electromagnetism. And so you see that at sufficiently high densities, you would get a contribution from the axion field to the charge density. And when this becomes competitive with what you might expect from standard astrophysics, then you start to get back reaction. And so this was studied by Caputo et al., and they found that you could actually get periodic shutting off of the pulsar activity, something that has been observed, and it's called pulsar nulling. And so this back reaction effect, they hypothesize may be responsible for this behavior. So you can actually see this pulsar nulling right here, where you see standard kind of pulsar activity, and then it just shuts off inexplicably. And then there's a little bit here, and then it shuts off again. And this phenomenon has not been understood, as far as I understand. And so maybe axions are playing a role in this. Okay, so everything up to this point, so here's the kind of parameter space that we have probed and expect to probe with these kinds of ideas. So the relativistic axions that just kind of free stream out, we can set a very kind of loose bound just by saying, let's not greatly overproduce the radio flux beyond observation, particularly between pulses, where there are very tight constraints on the radio flux. So I neglected to mention that one of the consequences of having an axion cloud is that it's dissipating in the form of narrowband radio emission. And this is basically set by kinematics. And so what you expect is a continuous narrow radio line coming from any active pulsar. And this radio line is not, it should be, again, quasi-isotropic, not really beamed like the standard pulsar radio emission. And a search for these lines, this is not a constraint, this is a projection. A search for these lines could even cut into QCD axion parameter space at higher masses. And finally, the range of parameter space in which you might expect axions to lead to pulsar nulling through the formation of this axion cloud is shown right here. And so at this point, you might just be squinting at this plot and kind of your eye might be drawn to this region where there aren't too many laboratory or astrophysical constraints. And so you might ask yourself, what is something that we can do to try to probe that parameter space? So I actually want to a really important point that I wanted to mention is that everything that I've talked to up to this point does not rely on axions being dark matter, or making up any significant fraction of dark matter. If they exist in your theory at all, they'll be populated in pulsar polar caps, and all of these phenomena that I mentioned should take place. But actually, some of the earliest work on this field of axions and neutron stars asked the question of what happens if you embed a neutron star in in dark matter. And so this has been studied by a number of people as early as 2009. And the idea that they found was that the axions would be pulled in, and some fraction of them convert into radio photons, and you would expect to see very narrow radio lines coming from these neutron stars. So just to say a little bit, to give a little bit more detail on this idea, we model neutron star, the plasma. I mentioned the importance of the plasma physics. And so I just want to give a kind of, a view of what the neutron star magnetosphere looks like. So you have these magnetic field lines, which you can separate into two different categories. Open field lines, which extend very far from the neutron star surface. And for reasons of causality, these field lines can't actually close back on the neutron star. And so instead of closing, they actually lag behind the rotation of the neutron star. This leads to the twisting up of those field lines. And that twist is what we think is responsible for powering the radio emission and other particle acceleration, non-thermal emission seen from that region. And then there's the closed magnetosphere, which is relatively speaking quite dormant. There isn't this excessive magnetic twist. You don't expect to see strong currents flowing in this closed zone. And it's pretty well described by this seminal model, which is called the Goldreich-Julian model, which tells you what is the amount of plasma you need in your magnetosphere to actually screen that rotationally induced electric field. And so what Axion folks do is they say, well, you have a spatially varying plasma around your neutron star. And I mentioned that if the plasma frequency, also known as the photon mass, coincides with the axion mass, you get resonant conversion. And in the case of dark matter, the photons that come out of this kind of resonant conversion are expected to be very narrowband. And this is set by the kinematics of dark matter. And so you might ask yourself, you can kind of get a sense based on what kind of plasma frequencies you expect around these neutron stars, what kind of axion masses you might be able to probe. And so just for some kind of prototypical values for a standard canonical radio pulsar of about 10 to the 12 Gauss and a magnetic field of about 10 to the 12 Gauss and a period of about 1 second, you get a plasma frequency near the surface of about 10 micro eV. And so if we want to push to higher masses, what can we do? So you might say, let's just crank up the magnetic field or lower the period, and maybe we can get there. And so if we crank up the magnetic field, we have these objects that are called magnetars. And you might at this point be thinking, are you really doing anything special? You just increase the magnetic field and you just use the same models. The goal of the remainder of the talk is to kind of disabuse you of this notion that magnetars are just pulsars with larger magnetic fields. And the transition from pulsar to magnetar is, you could think of it as kind of, is it arbitrary? But no, the answer is not. There are actually fundamental scales that you cross when you go from a pulsar strength magnetic field to a magnetar strength magnetic field. So for example, one of those important scales is the electron mass squared. The magnetic field corresponding to the electron mass squared is about 10 to the 13 Gauss. And when you cross in, when you go above this what's called the critical magnetic field, standard QED processes are kind of modified. So Libby showed that plot of the cascade happening in the pulsar polar cap. Now, if the magnetic field is in the supercritical field range, then some of these processes are modified, and this can have dramatic effects on the emission of electromagnetic waves and even axions. In addition, we talked about magnetospheric twist in pulsars. This, we said, was localized to those open field lines, which are lagging behind the rotation of the neutron star. But at such strong magnetic fields, once you go to 10 to the 14, 10 to the 15 Gauss, we know that magnetic fields are like, they're like ropes that have tension. And if you increase the tension of that rope, it can actually break things. And this is exactly what's expected to happen, is that the magnetic field lines can actually break the crust of the neutron star and give rise to, this magnetospheric twist all over the surface of the neutron star. And this behavior is actually well supported by observation. So high field magnetars exhibit considerably different emission characteristics from standard pulsars. So for example, they're highly dynamical. They show these crazy bursts and flares, including quite recently, we've been able to associate some of these fast radio bursts with magnetars. And in addition, they show hard X-ray emission, and by hard here, I mean more energetic than just what you would expect from thermal emission. And this is highly indicative of some either particle acceleration or other exotic processes. And so I mentioned the importance of some of these QED processes that occur only in very high fields. I'll get back to this in a couple of slides. So at present, not enough is known about magnetars to say anything conclusive about possible axion signatures, but we actually do understand quite a lot about the kind of general structure of magnetar magnetospheres. And there are kind of two camps that people fall into, and it's basically where this twist is. I mentioned there's some twist in the magnetosphere. Some people suggest that this twist occurs on very large scales, that the twist is located close to the magnetic poles. This is what is called colloquially as the J-bundle model. And then there's the idea that these small-scale twisted loops can be scattered all over the surface of the neutron star. And this is actually what happens in the sun. If you've ever seen a GIF or a picture of these solar loops that slowly twist and then they eventually break to give rise to solar flares. Again, physics related to magnetic reconnection that Libby was talking about before. The same kinds of loops may be there in magnetar magnetospheres as well. So let me talk a little bit about each of these models. So I mentioned, even if I give you the kind of arrangement of the magnetic field lines in the surface of the, or in the magnetosphere of the magnetar, I still need to give you information about the plasma state. And so this is something that people worked on about 10 years ago. And so the idea is that if you have a sufficiently low electron-positron density in your magnetosphere, and I take a little bundle of field lines and I just twist it, and by twisting, what I mean is, you imagine I just take the kind of surface and there's a little disk of field lines and I just literally twist that disk. That's one way to think about what this twisting is, what that twisting is. If I have a sufficiently low plasma density, then an electric field will develop. And this electric field can accelerate particles to high energies. And the energy that they reach is set by what's called resonant inverse Compton scattering. And the idea is that these accelerated particles are seeing thermal photons from the surface of the neutron star. And at a characteristic gamma factor of about 1,000, in the rest frame of those particles, those keV, roughly keV photons, have the energy that's equal to the spacing between their Landau levels. And so this can excite an electron to a higher energy state, and then it can subsequently decay into its ground state, a high energy photon, and that photon can then create more pairs. And so basically what we do is that we kind of study this physics on a global level. And again, I don't want to go into too much detail, but here I want to show a plot of what the expected effective plasma frequency is in the surface or in the magnetosphere of a magnetar. And I won't get into all the different terms here, but I actually want to just draw your attention to this plot, which shows that you are seeing plasma frequencies of about 10 to the minus 3 eV, whereas you might have only expected maybe 10 to the minus 4 just by naively scaling up the magnetic field in the Goldreich-Julian model. So this is just a statement that this is there are qualitatively different effects happening when you go to these large magnetic fields. And another example of that was demonstrated in these models that study these small-scale loops. And by small scale here, I mean that they extend not far enough from the surface to see a considerable change in the magnetic field. So everywhere in a little loop like this, you expect a very strong magnetic field. And so in such strong magnetic fields, qualitative changes to QED processes take place. For example, you have enhanced collisions. And basically, just to kind of condense this, you can imagine electron-positron scattering through the S channel. And if that now in a sufficiently strong field, that intermediate photon can actually be on shell, because you don't need to electron-positron to single photon is now kinematically allowed, because you don't need to preserve momentum conservation. And so this gives you a huge enhancement in the E plus E minus scattering cross-section, and this makes the plasma a lot more collisional than you might have expected if you just use a standard, let's say, Thomson or even Klein-Machina prescription for electron-positron scattering. I don't want to say too much more about this, but one more thing, I guess, is that now you can even have an enhanced photon-photon to electron-positron pair creation, because the kinematics, again, the main thing in being in such strong fields is that momentum conservation becomes considerably relaxed, because in a magnetic field, the vector potential gives a contribution to the conjugate momentum, and this allows you to do things that you might not have been able to do in a vacuum. And so putting all of these processes together allows you to derive an equilibrium plasma state. And this is work by Jonathan Zhang and Chris Thompson at CETA. And what they found is basically plasma profiles where near the surface, the plasma frequency can reach almost 10 to 0.1 eV or so. And so again, these are much, much higher plasma frequencies than you might have expected in the Goldreich-Julian model. And so what we can do is then try to see what we expect from Axion dark matter conversion around these objects. And so what I'm showing here are two different models. One here is the first model that I talked about, this so-called J-bundle model, in which you have a fairly low electron-positron density that allows the formation of electric fields. And here is a particular geometry, which is, where are you? Here, this quarter model, which shows a magnetic field loop that extends over about a quarter of the azimuth of the neutron star. And there are similar plots for other models that are all roughly kind of in this range. And so what we can see is that if it is really something like the J-bundle model, we actually, with future observations, we can actually get very close to probing much of the QCD Axion parameter space in the kind of 10 to the minus 5 to 10 to the minus 4 EV range. Whereas the prospects at higher masses are still challenging, even even with kind of future observations. But of course, I think all of this stuff relies on better astrophysical modeling of these magnetars, which is a very active area of research right now in high energy astrophysics. And so just to conclude, and partly to advertise for some of the topics that I'll discuss in my discussion section, we said that rotationally powered pulsars are great factories for axion production and conversion in roughly this range, and even possibly for the QCD axion. And pushing to higher masses, magnetars give us kind of great prospects for this, but we really need to understand the astrophysics of magnetars better to kind of break the modeling uncertainties. And finally, this is kind of a coordinated effort between astrophysicists, particle physicists, and plasma physicists to characterize the distribution of electric, magnetic fields, plasma distribution functions, and then modeling axion-photon mixing in these settings. And so with that, I will conclude and then take questions. Thank you.
Thank you, Ani, for your great talk. Let's take a question from Kara first, and then Marius.
Ask a couple of clarifying questions. So all of these different models you were showing for the magnetar twist, are these all hypothetical models, or okay? And so okay, so then the details that you were giving us about each of these models, these are like things we would see if this is realized in nature?
Yeah, so I went over this kind of quickly. There are observations that have some support for one model or another. Okay. So actually, I should say this J-bundle model here. So for this particular magnetar that we are looking at, there's a phenomenon that was predicted by this J-bundle model that was then observed in this magnetar. It's what's called shrinking hotspots. So you see the bases of these field lines. You expect particles being accelerated there, and they bombard the surface and heat it up, and so you expect hotspots at the bases of those field lines. And as they study that as these things evolve, those hotspots shrink. And this is actually something that's been observed in this particular magnetar. I wouldn't elevate that to the level of saying that we have, we're doing precision physics here, but what was your?
Yeah, so I guess I'm curious how we would go about distinguishing these different models, and if it's possible that some magnetars obey some models and other magnetars obey others.
Yeah, so this is a great question. Yeah, so how we could use observations is that basically where these things live are sites of non-thermal emission, and specifically this hard X-ray emission, which is phase dependent. So as the thing rotates, we see that hard X-ray emission being modulated at the rotation frequency. And so this is actually what NICER does. NICER isn't actually doing spatial resolution, they're doing time resolution as the thing rotates. And so if we had some hard X-ray phase-dependent data from a magnetar, then we may, once we better understand the connection between these and that hard X-ray emission, which is something that people are kind of already doing, then we actually might be able to use that phase-dependent hard X-ray emission to actually map where these loops are. Yeah, and this is done in neutron stars, and I think it's even been done in a magnetar. NICER has done one in a magnetar. Oh, okay.
You said at the beginning that some of the axion densities were like 10 to the 23 Jev per cubic centimeter, right? Which is like ridiculously big.
Yeah.
I know like those deltas that you had in the Hamiltonian at the beginning for the mass mixing.
Yeah.
Right? I mean, those are like forward scattering from the photons, right, with the background medium. And those go as the number density of background, electrons or whatever, right?
Yeah.
Or the Euler-Heisenberg term for the magnetic field. But there are also terms in principle, like the axion forward scatters with other background stuff, and that can go as the density of the axions, especially if it forward scatters with itself or so on.
Like
and
axion
usually it's suppressed by FA a lot, but the densities is ginormous.
Yeah.
Right.
Yeah.
And I still think it's small, but like it's like it's just like a super quick estimate. It seems like it's comparable maybe to some of these Axion masses, but I don't know. Like, what are the
Yeah.
plasma masses that you're dealing with?
Yeah, so the nulling thing that I mentioned is basically that when those Axion processes become competitive with standard model processes, self interactions, like you said, suppressed by FA. So you can, those densities that I talked about, you can call that like a theta angle, and if you translate that to a theta angle for the QCD Axion, it's like 10 to the minus 8 for, 10 to the minus 7 maybe for 10 to the 22 Jeff per centimeter cubed. And at a theta of 10 to the minus 7, you're not really yet getting to a regime where self-interactions are important, unless there's something that I'm missing. So if you have an idea, let me know. But I think they're high, but not high enough to worry about self-interactions, as you would in like a super radiant cloud. But still, there are interesting things that can happen as you say modify. Anyway, I won't speculate. I'll save that for my discussion section. Yeah.
Shobik?
Yeah, so again about pulsar nulling. So is that what you showed? Look like the nulling constraints and yeah, this one. Yeah, so these two constraints, they seem to be somewhat sensitive to different axion masses. Is there a quick way to understand, especially like why the nulling constraint is more sensitive to lighter?
Yeah, it's more the time scale. So that I think what this is also not a constraint. It's just like this is where the parameter space where you could explain nulling. And I think it's basically that it's seen on time scales that, those observations of nulling that I showed are seen on time scales that correspond to, let's say, 10 to the minus 9 or 10 to the minus 8 EV axions. But also, if you fix the density, the axion amplitude is larger at lower masses for fixed density. And so those you would expect would have, at the lower masses, coherent effects over that whole gap. If the axion wavelength is longer than the gap size, you would see like a coherent axion-induced electric field. And that is generally better than having, small-scale incoherent axion effects over the gap. Yeah, so it's set by, this is basically the size of the gap, 10 to the minus 9 EV. Yeah.
Honey, I have a question since I have the microphone.
Yes.
The gravitationally trapped particles around pulsars, can you extend that study to magnetars to go up to higher masses? Or what changes?
I would like to, but I don't yet know how to produce axions in magnetars yet.
So they don't have this polar cap phenomenon?
They might. So they should, but the polar caps for magnetars, at least the ones we've observed, are really small because the radius of that cap is inversely proportional to the rotation period. And so far, the magnetars we've observed are really slow. So you can do the same calculation, assuming, and of course that assumes all the QED physics remains unaltered, which it doesn't. And it tends to be worse than pulsars. But in, for example, this J-bundle model here, these loops are actually quite broad, and that's supported by radio emission that's seen in the few magnetars is much broader than, like, the beam is much broader than you would expect from the polar cap. And so I think that you can produce axions in these J-bundle beams, but there's a kind of uncertainty about how well this model actually describes magnetars. So that's something that we're still trying to figure out.